Hello and welcome to the next part in our Simple Science series where we take some of the complex questions in Formula One and simplify them. Today we're going to look at one of the most complex parts of a Formula One car, which is the power unit. And today we're joined by Hywel Thomas, the F1 Power Unit Director from Mercedes-AMG High Performance Powertrains. Hal, thanks for joining us first of all. This is going to be a fantastic insight for all of the fans that have got, whether it's a basic understanding or an advanced understanding of an engine. There's going to be a lot of tough questions, so let's see how far we can get.
Okay, let's do it.
First of all, we're just looking at a standard engine. Where does the actual power come from in an internal combustion engine? What's the cycle and process?
The basic process of an engine, and the one that's used in Formula One and most road cars, is the four-stroke cycle. What are those four strokes, and how does it happen? I've got a crankshaft here, which is my single-cylinder crankshaft, not from a V6 engine, but from a single-cylinder development engine. And what I'm trying to show here is that there's an offset. You can, if I can hold it properly, you can see there's an axis of rotation, and then there's this offset crank pin. We connect from that offset crank pin via a conrod to the piston. And the stroke is when the piston moves from the top of the cylinder to the bottom of the cylinder, or from the bottom to the top. A four-stroke cycle is one movement down, up, down and up. And that corresponds to two rotations of the crankshaft. What are those four cycles? There's the induction stroke, the compression stroke, the power stroke, and the exhaust stroke. Or as they're more affectionately known, suck, squeeze, bang, blow. Start with the induction stroke. Piston at the top of the cylinder, it starts to move down, the inlet valve's open, and it moves to the bottom of the cylinder, so that's its first stroke. And what's happening there, the pressure inside the cylinder is slightly reduced as the piston moves down, and the air in the plenums, prepared air ready for combustion, is then rushes in because of the pressure difference between the cylinder and itself. Also during that stroke, as the GDI engine, and the fuel gets injected directly into the cylinder. So what we end up with at the bottom of that stroke is a nice air-fuel mixture. We close the inlet valves and we compress it. So that's the second stroke, compression, squeeze. So what's happening there is volume of fuel and air is getting compressed and getting prepared. The pressure goes up, the temperature goes up, everything's ready, and it's just waiting to combust. And then nearing the top, we then spark the spark plug and we get a combustion event. So that beautifully ready, prepared air-fuel mixture will then combust and you get the power stroke. So the piston is then driven to the bottom of the stroke, and that's where via the conrod and that offset crankshaft, you then get a torque applied to the crankshaft, and that's where the power's coming from. And what you then need to do is get rid of all that's left, because you can't burn it again. So the exhaust's open, and the piston moves up again, and it's expelled through the exhaust pipe. That's the basics of a four-stroke cycle.
So that's your suck, squeeze, bang, blow.
Exactly that. It's as straightforward as that. Hard to forget.
So during those processes, what sort of forces or temperatures are we talking about?
The combustion loads from that controlled explosion they're quite incredible when you stop and think about them. So the pressure wave that forces that piston down, it's the equivalent of having four elephants sat on top of that very, very small piston. The temperatures are sort of in the region of 2,750 degrees C, and that's half the temperature of the surface of the sun. And then you've got to think how quickly this is all happening. If you blink your eye, which you will have done now because I've said it, those combustion events are happening 200 times for our whole engine.
200 times in the blink of an eye?
If you multiply that up for a qualifying lap, we have 50,000 of those events in the engine happening over the time of a qualifying lap. Car go out and trundle along the pit lane getting ready to do its qualifying lap. What I'm thinking about is those 50,000 times we're going to get four elephants sat on top of our pistons, and the temperature's half of that of the sun, and all the work that's gone in to make sure that we can hold it all together.
With all those temperatures and all of those elephants, an F1 engine, or indeed just a performance race engine, is going to be completely different from our road cars. But what's the main differences? Is it the materials? Is it the design?
I think it's very hard to say, because actually the components themselves, as you can see from yours in the background, are incredibly similar. There will be a crankshaft, there will be a rod, there will be a piston, and that will be there in every internal combustion engine. But yes, the design is very different. The calculations that have gone in to understand how we transfer those 4 elephants from the top of the piston to the crankshaft, all that understanding and the way we work with Petronas to make sure that the bearings all work. There's just that level of detail of the understanding, and also, you're quite right, the materials, being able to take the materials to the next level that maybe you can't in a road car. The fundamentals are the same. It's the details and the innovation that's being put into them that make it different.
One of the things when we're travelling around from circuit to circuit and country to country, we talk to the fans, and sometimes the fans will ask us how many horsepower has the car got, but you'll go to a different part of the world and somebody will ask how much torque has the car got. What's the difference between horsepower and torque, and is one more important than the other? What we sort of chasing in Formula One?
Torque is something that's quite straightforward to think about. I think you've got, if you think about your spanner on a nut and you're tightening that nut, you've got the force, which is you're putting on the force, and then you've got a distance between you and the nut, and the force times distance is the torque. And it's sort of the same in the crankshaft. If you think about, we've got that offset pin, you've got the rod coming down, so it's a force offset, and so you've got a force and a distance, and that's what creates the torque on the crankshaft. Power, on the other hand, is very closely related to torque, but it's the amount of torque you can have per unit time. So torque is the work done, power is the work done per unit time. So if you think of a car that's coming from a low speed corner exit, trying to get to the start of the next corner, torque will be the amount of work done to get it to the next corner. Power is then when you start talking about time. And it's the more power, the quicker you can get to that next corner, because it's work per unit time. So really, in Formula One, we always talk about power.
Power.
Power. Give me more power.
Is that what the drivers are always asking for?
Yeah, I've never heard one not ask for it.
Now, one of the things that I've noticed on some of the onboards is when the drivers change up on the gears. Now, in the regulations currently, we're allowed to rev to 15,000 RPM. I know that the regulations have changed over the whole 70 years of Formula One. But with regards to the drivers changing up, sometimes they're trying to change up a lot lower than that, maybe 10,000 or 11,000 RPM. Why aren't they using all of that power or all that RPM?
The power relative to the RPM isn't a straight line. It's a curve. There's a peak power somewhere around 10,500, 11,000. What you really want to be doing is getting as close to that peak power and using as much of that power with your gear changes. So the whole intention of that gearbox is to keep the engine operating right in its area of peak power, which won't be right up at 15,000. The reasons that that's the case, below 10,500, through regulations, you can put less fuel in. So there's a regulation that just allows you to linearly goes up in fuel flow and then flattens out. And it flattens out at 10.5. Below that, it's influenced by that. Above that, you start getting influenced by friction. So friction, the amount of force and rubbing that you lose through bearings, that goes up with speed and some parts speed squared, so that all of a sudden the friction is getting much, much higher. So that means that after that, you start to dip off and roll off the power. So it's that shape of the power curve that's being matched by the shift point.
So how often we hear the drivers talk about something called derating, but what is derating and what's actually happening to the power unit when we hear that term?
We are deliberately turning off the MG UK, so deliberately turning off the 120 kilowatts additional boost that you can get from that electric motor. We do that at the end of straights sometimes, and that's what the driver's feeling, and all of a sudden that loss of 120 kilowatts of power. So the obvious question is then, why on earth would you do that? Why would you reduce the power of the power unit's supplying? And the reason we do that is that we've only got a certain amount of energy that we can deploy. Either in some circuits that's regulation-based limit, and other circuits it might just be a layout-based limit. But basically there's a certain amount of energy you can use. And you have to choose where you use that energy. If you look at the graphic now that we've got, this is what we do with every circuit ahead of going there, is map out where are we going to use our energy. So the colour coding here, blue is when we're either harvesting or part throttling as the driver is going through that corner, and then green is when we have maximum engine and MG UK power, and then red is that's where the derates are. So if you can see from the sort of top middle point of the lap where the little circle sort of shows the start finish, that end of that straight we would be derating, and then harvesting, and then we go all the way up that long hill. Most of it in the green zone, so most of it with the engine and the MG UK, but then there is a derate, and then we go around the corner, and then you're into that area again. Why do we do it at the end of the straight and not the start of the straight? At the start of the straight is the maximum sensitivity to power. So the maximum amount of lap time reduction you'll get is by using your power at the start of the straight, not at the end of the straight, and that's why we do it.
So what would be the difference between what you called there a neutral lap and a qualifying lap?
It's a very similar graphic, except you'll see that the derates are far, far more reduced. We're not using the derates of the red piece, but what you then get is the sort of pinky magenta bit at the start of straight. And what that is doing is that's when we're going to AMG turbo mode. So we've got the wastegates open, we're not using the turbine to harvest energy, we're actually powering the MGUH to create the compressor. So it's very energy hungry, but that's our absolute ultimate performance mode. And we do that right at the start of the straight, as I've said earlier, because that's the part which is the most sensitive to power and lap time.
Sometimes we hear the race engineers, they talk about the strat mode, but other times they mention something HPP or high performance powertrains. What's the difference between those two settings?
The strat mode is a very simple switch for the driver to get to, and it's very obvious, and it has quite a small number of positions. And what we do is we collect up a number of settings and put those on the strategy switch. Qualifying mode and using the energy in this way is on one strategy, and then maybe a race neutral lap, that will be on another strategy mode. So it's a collection of settings which mean different performances out of the power unit. The HPP mode is the next level down, where you need to maybe change some of those settings within the collection to get it to do exactly what you want. Typically it means if we're moving HPP modes, it means we've got something a little bit wrong at the factory ahead of the event and we need to change something.
I suppose we've got all of the team back at Brackley with the race support room looking at the chassis and a lot of the strategy, but how can you actually react, and how quickly can you react when there's, as you mentioned, there's different planning? What if there's a safety car? What if there's a change in weather? How quickly can Brixworth actually react?
Some of those things are relatively straightforward. A safety car will have a strat position because we know 2 races out of 3 we will be using it. It's worth doing. But there are definitely other things that we won't have been ready for. Something odd's happened, maybe something odd's happened to the car or the power unit, which means we need to change some settings. We're in the same position at Brackley, where we have what we call the TSO, which is the track support office, and we have engineers there. They've got live data coming directly from the circuit. They've got intercom link back to the circuit. And so we've got more eyes looking at the power unit back in Brixworth. And we can react relatively swiftly. We can react as quickly as the human can react to understanding what's happening, coming up with a plan, and then relaying that back to the circuit. You think you're doing it very, very quickly. You look up and 3 or 4 laps have gone because it's only 1.5 minutes per lap. And it is hard to do it in the blink of an eye, but we have got the people and the resource ready to react as quickly as is humanly possible.
Really great insight. Just before we move off of strat modes and HPP, I know there's going to be a burning question on the lips of all the fans. Is there a party mode? Does it exist?
The party mode is our qualifying mode. That's the mode that has the most engine performance and depletes the energy the most. That's the party mode, and yes, we have got that mode where Strat 2, that's the mode, and everyone knows when you go in Strat 2, you're in your qualifying mode, and it's your party mode.
Do we call it party mode?
We don't know. It's Strat 2.
Strat 2. I mean, obviously that changes, doesn't it? If any other teams are listening, Strat 2 is not always our party mode. Just to move back to some of the science of the power unit, one of the things since 2014 that is really revolutionised the future, not just of Formula One, but of also road car technology, is the thermal efficiency that we're getting out of the power units now. And I know certainly at Brixworth you've been really pioneering this. But what is thermal efficiency and why is it so important?
If you take the amount of energy that is tied up in the fuel and the rate that fuel is being supplied to the engine, you've got a certain amount of energy, and if you then convert that to power by using time, you've got a certain amount of power that's possible to release from the fuel. And we can measure that, Petronas do measure that, so that we know exactly how much energy is available. We then burn that fuel in the four-stroke cycle, and we then measure how much power we're getting out. So it's very simply the ratio of the amount of power that's coming out to the potential power that you put in with the fuel.
So I suppose in the simplest terms, it's more bang for your buck.
That's why it's so important on a road car. It's less waste energy. For us, the regulations say you can only use a certain amount of fuel per second. So if your thermal efficiency is higher, you're getting more power out of that certain constrained amount of fuel. You're creating more power than your competitors.
That leads us nicely into our next question. We've got the engine and the power unit, obviously, but then there's also the fuel from Petronas, our partner. We've had so many different blends of fuel over the years. I mean, if you go back to the Grand Prix era of the silver arrows in the 30s, where we were using methanol and ethanol and acetone, things have moved on massively since that. But how much of a difference does having a partner like Petronas make when it comes to fuels and lubricants?
We're very fortunate that we work incredibly closely with Petronas. We have great links, and it's personal links between our engineers and engineers in Malaysia and engineers in Italy from Petronas, and their combined understanding of the way that the combustion works in our power unit and the fuels. That means that you can really understand how to make very subtle changes within the fuel composition that will then allow us to have thermal efficiency or just straightforward power.
There's a term, and I'm going to embarrass myself now because I should know this, but this is not a joke, what is engine knock? Is it quite literally something that sounds as if it's knocking?
What engine knock is, we can go back to the four-stroke cycle, when you have that compression stroke of the fuel and air. So what I described earlier on was, as we get to top dead centre on that compression stroke, we spark the spark plug and you get a small flame kernel. And then that small flame kernel very quickly expands, burning all the fuel-air mixture, and it does that in a beautifully controlled way. And although we talk about a large and high increase in pressure, it's actually done in a very controlled way. And we spend a lot of time with CFD and simulation and measurements and testing to make sure that we get that very, very controlled combustion event. Knock is when you have an uncontrolled combustion event. So what happens is, during that compression stroke, as you get to the top, there may be, if you haven't had the mixture preparation right, if there's maybe a physical hotspot on your piston or even on the cylinder head, you might get to a point where that very, very local pressure and temperature means that before the flame actually gets there, you have this uncontrolled combustion event where you have a very local detonation, and that causes an incredible shock wave that then goes through the cylinder. So it's uncontrolled combustion is what knock is. And when we talk about the pressures involved in those sort of things, very locally, you can erode the pistons, and actually the amount of force that then puts through the whole system can be quite horrific.
How can you actually tell, though, it's knocking? Can the drivers hear it, or is there any sensors on the car that you can see?
From the engineering perspective and looking at the data perspective, yeah, we can measure it. We can measure it through cylinder pressure, and you can actually measure it through the acceleration of the cylinders. You can feel that knock, that pressure wave going through the cylinders. But can the drivers hear it? Yeah, they definitely feel it. It's interesting, when we go out in qualifying mode, the drivers love it because all of a sudden they hear the knock and they understand then this engine is right on its limit and it's working really hard for me and it's giving me everything that it's got. So they enjoy the knock and they think that's the engine going well. From the engineers, we're there with our heads in our hands going, this engine is right on the edge of going very, very badly wrong. So we're trying to make sure that, and it's just a different way of looking at it, but they hear it, they definitely hear it.
The drivers are turning it up to 11 and loving it.
Yeah, exactly that, yeah.
Look, finally, one question. I mean, the block that I've got behind me here, this is an old 3-litre V8. I know we've had the fantastic era of the V10s and the V12s, which sounded fantastic, but now we're getting smaller and smaller engines. I know it's been the age-old question, size, does it really matter? But how are we actually achieving more power out of a smaller engine, almost half the size of this engine?
This is the trend of road cars, and it's what's happened in Formula One as well, where you turbocharge an engine rather than making it naturally aspirated, and that allows you to downsize. So if you imagine when we were talking about the four-stroke cycle, and we were talking about when the piston on the induction stroke created a delta P in the cylinder, which then meant that the air could come in. If you're turbocharging it, you're increasing the pressure at the point of entry so that you're ramming in as much air as you possibly can, which allows you to put more fuel in, which therefore means that you're getting the same amount of force through the crankshaft and the same amount of torque through the crankshaft as if you had more cylinders but was naturally aspirated. So it's this real sort of skill of reducing the size but making the bang the same.
How much more power do you think you can actually get? Can you go smaller and give us even more?
That's always the challenge, and that's always what we've been doing. And every time you think perhaps we're getting close to the edge, the teams work their socks off and they're innovating and they're working so hard that somehow they find a way of getting that extra little bit of performance. There are some limits to it. The four-stroke cycle has got a position where theoretically you can't beat it. And you know what? When we get there, we'll try and find a way of going past it.
Well, Hywel, thank you very much for your time today, and thanks for giving us an insight to a little bit more information about behind the scenes at Brixworth and how we bring that power through innovation and design.
No problem. Thank you very much. It's been a pleasure.